Well, so first of all, thanks a lot to the organizers for letting me give this talk. My name is Yeray Garcia Castillo. I am currently a PhD student at UNSW Sydney, and I'm going to give a small talk about the influence of quadratic axion-matter interaction on the direct detection of dark matter. So this talk is based on two papers. The first one was done in collaboration with Claire Burrash, Benjamin Elder, and Jörg Jekyll, my master's supervisor in Heidelberg. And the second paper was done in collaboration with Benjamin Hamed and Jörg Jekyll. Well, first of all, let me do a small introduction. As you know, there are several astrophysical observations that cannot be explained without the presence of a new form of matter. This is what we call dark matter. So basically, rotation curves of galaxies, large structure formation. All these observations point out the existence of a new form of matter that we have not detected yet. So they are pointing in this direction, and in this context, axions and axion-like particles arise as well-motivated candidates for this new form of matter. So why do I say well-motivated? Well, in the case of axions, they were first introduced to solve the strong CP problem, and then it was realized that they could be good candidates for dark matter. In the case of axion-like particles, they can be motivated through different models. For instance, in string theory, when extra dimensions get compactified, a bunch of scalars appear, which have normally light masses. This is a way of motivating these axion-like particles. But for us, the important thing is they have these three features. So they are scalars, as I have already anticipated. So they have spin 0. Then we know they have light masses, so we are considering basically this range. Masses much smaller than WIMPs, for example. And they can be treated as wave-like classical fields. So due to their large occupation number, quantum fluctuations of the field are small. So a classical field treatment is totally fine. And that's what we will carry out in the next slides. These kind of particles can have this coupling here to the strong sector. So phi is basically our axion-like particle field, Fa the disintegration constant, Gs the strong coupling, and G and G dual are the field strength tensor of the gluons, basically. As we know, QCD has a non-trivial vacuum structure, so it confines, and below the QCD phase transition energy, this coupling is going to produce a potential for the axion-like particles that is going to get modified by nucleon densities. So since QCD properties are modified in medium, the potential for the axion-like particle will also be modified in medium, leading to this potential here, which depends on these quantities, depending on that are QCD quantities, so basically the pion mass and the disintegration constant of the pion. The important thing for us is that rho appears here in the potential. So for small values of the field compared to this disintegration constant of the axion-like particle, we can derive this Lagrangian here. So we have basically the kinetic term for the scalar, the mass term here, so basically the usual Lagrangian for a scalar, and then this additional interaction with the nucleon densities, which is quadratic in the field. That's the interesting feature. Here we have introduced lambda as a parameter to parameterize the strength of the coupling, and from here we can basically derive the equations of motion for the scalar, and we arrive to Klein-Gordon basically plus this new interaction with matter, with the nucleons. This equation has a really interesting phenomenology. It has been already studied by different people. And why is it interesting? Well, because matter densities, so ordinary matter, is going to modify the axion-like particle field distribution. It's also important to notice that this quadratic coupling we have shown here, motivated by this gluon coupling, can also be generated through other portals. So, for instance, if the scalar couples to the Higgs, one could in principle have this quadratic coupling, or in any model we could have this. So for our purposes, we will keep this lambda free, basically. So an interesting consequence of this coupling that we have studied is the modification of the detection sensitivities. So when we aim to detect dark matter, basically we want it to interact with fields we already know from the standard model. So for instance, CASPEr electric aims for the interaction between the dark matter and the EDM, so electrodipole moment of nucleons. Or for example, BRED would aim for the interaction with the electromagnetic sector through this FF dual term. These two experiments have in common that the interactions are proportional to the field, so phi appears linearly. And what we want to say is like the Earth as an object made out of nucleons, or in general as made out of matter, can affect the sensitivities of the Earth detection. So let me explain this with this drawing here. Far away from matter sources, the field should behave this way, basically, because we have the usual Klein-Gordon equation, where phi 0 is a constant amplitude of the oscillation, which is given by the condition of having the local dark matter density, energy density from this scalar field. However, as we get close to the Earth, the interaction is going to matter, and normally where we carry our experiments is on the surface. So as you can see here, the amplitude of the field gets modified on the surface if we have this kind of interactions. So in this case, will be suppressed. So basically what we want to say is that if we use the value of phi 0 to do our estimations of sensitivity, we are being too naive, because basically the Earth affects the field profile since it's made out of nucleons or matter in general, and we should do our estimations with the value of the field at the surface, so this value here. The same can be applied to experiments that aim for interactions proportional to the gradient. So basically CASPEr wind has an interaction of the gradient with the nucleons, and the same story applies. So if we take the gradient naively of this simple solution of the Klein-Gordon equation, we are being too naive, the Earth is affecting, and we should do the estimations with the value of the gradient at the surface of the Earth. So here. So how does this look like? Well, here I'm showing the field profile for different values of the coupling, always repulsive, so we have lambda bigger than 0, in the zero velocity approximation. So basically here we are considering that the dark matter is static compared to the Earth, to our frame, which is not realistic, as we will see, but for an illustrative purpose is good enough. So what we see is that as we increase the coupling, the amplitude of the field at the surface gets suppressed. So the larger the coupling, the more suppressed is the field at the surface, and the gradient gets enhanced. So as you can see here, the slope gets bigger and bigger as we increase the coupling, basically. For attractive one, the contrary is realized. So as we make the coupling more and more negative, the field value increases at the surface of the Earth. So here you can see it. And the gradient also gets enhanced, as you can see with the non-zero slope. As I have said, this zero velocity approximation is very naive because, we know that the solar system is not static with respect to the dark matter. We are moving towards signals with a non-trivial velocity, 200 kilometers per second actually, and we expect a flux of dark matter. So a more accurate picture is imagine the dark matter coming as a plane wave with a certain momentum. The wave interacts with the Earth, and the amplitude of the field will get modified basically near the sphere, the matter sphere, which is the Earth in our case. So this tells us basically that our differential equation is of course correct. It's totally general. However, we need to change our boundary condition. So the boundary condition here we consider here is this one here, we consider an incoming plane wave given by this term here, and then this is basically the modification of the field. So the Earth is going to modify the incoming wave, and we want to quantify how the amplitude of the wave is changed. This picture we have presented before is still a bit naive, because, as you may know, the dark matter has a velocity distribution. So instead of imagining a plane wave, we should imagine more a wave packet with a certain dispersion, which is given via Gaussian to a good approximation. So we will have a bunch of modes of plane waves interacting with the Earth and modifying the amplitude and being modified by the interaction with the Earth, basically. To treat this problem properly, we need to calculate the power spectrum. So, as I have said, we have different modes. Each mode has a random phase, so we have an stochastic field. And we can describe our field in this way. So we have basically a factor that weights each mode given by this Gaussian distribution. Then we have the plane wave here with the random phase. So alpha is a random phase that depends on each mode. And we integrate this over the phase space, basically. From this, we can calculate the power spectrum for the gradient. So we do the usual. We calculate the 2-point function of the gradient and do an ensemble average of it. And yeah, basically doing the Fourier transform of this 2-point function, we will arrive to the power spectrum. Here we are showing basically the power spectrum normalized by the free power spectrum. So the free power spectrum is just the power spectrum we would obtain without this interaction. And well, yeah, we are integrating over frequency, so the total power spectrum, so to speak. We are representing this quantity in the parameter space. So here we have the mass of the scalar in the x-axis, and in the y-axis we have 1 over Fa, which is proportional to the coupling. So the higher 1 over Fa is, the higher the coupling is. And we see that in a big region of the parameter space, we get an enhancement of the sensitivity of several orders of magnitude. Here you may notice there is kind of a cutoff in the mass, which is related to the fact that for basically the Broglie wavelengths of the dark matter that are much smaller than the Earth, we don't expect any effect at all, as we would expect naively, of course. For the attractive coupling, we see basically the same. So we see an enhancement of the sensitivities in this region. However, we see here more interesting profiles, and this is related to the formation of bound states. So in the same way as in a quantum, like in a basic quantum well, if the attractive coupling is strong enough, we can have bound states. The same occurs in this treatment. And this is going to produce like higher enhancements of the power spectrum at specific places. So you can see here a bit of enhancement. But yeah, in general, the region is kind of the same, except for these bound states. The important thing is that we have an enhanced sensitivity for these experiments looking for gradient couplings. And if we look into CASPEr wind, for example, we see that in this region here I'm showing, we will have an enhancement of the sensitivity. So basically in CASPEr, 0 to ultra low field, a bit in phase 1, and yeah, a bit in phase 2 also. So yeah, this is the region where we expect enhancement of the sensitivity. Now I want to speak about a slightly different topic. So far we have looked into stationary solutions. So the time dependency was trivial, was just oscillating. Even though we were considering like a relative velocity between the dark matter and the Earth, so far we have used stationary solutions. However, we can ask ourselves if these solutions are good enough, because, well, as you know, the Earth is not in a stationary configuration. The Earth is in an accelerated movement around the Sun, So we want to see how good are these solutions and if we would need to consider effects like this one. In order to do this, we want to understand the timescales of the field and how it relaxes to stationary configurations. And to do this, we have studied very simple physical situations that capture the timescales. The most simple situation one can think about is the appearing source. So we start with an homogeneous field with a constant amplitude everywhere in the space. We pop up a sphere and we want to see how the field relaxes to the stationary configuration due to the appearance of the source. Why is this interesting? Well, it has a non-trivial time dependency and it's kind of a simple situation. That's what we wanted. And it's kind of related to the accelerated source situation. So basically you can imagine the Earth moving in steps and the field relaxing to the stationary configuration in each step. I know this is not, it's a bit naive of course, but we at least think it captures the relevant timescales. We did this with two methods, semi-analytical one, calculating the eigenfunctions of the differential equation, and numerically. So we just solve the equation numerically for the appropriate boundary and initial conditions. Here I'm showing a plot comparing both. So here I'm plotting basically the difference between the amplitude of the field and the amplitude of the stationary solution. So basically we expect this difference to go to 0 as we approach the stationary solution as a function of time, normalized with the mass. We are choosing some parameters for the source, but this doesn't really matter. And what we see is that looking at the relaxation at different radii, the two solutions match very well. So here, the solid line is the numerical solution and the points are the semi-analytical one. And as you can see, they match almost perfectly. An important thing we can see here also is the scaling of the asymptotic behavior. So we have drawn these dashed lines to guide the eye with 1 over square root of t behavior. And as you can see everywhere, the field relaxes with this behavior. So 1 over square root of t. At this point, we wanted to go a step further and basically obtain an analytical expression for the scaling. We knew it was 1 over square root of t, but we wanted to get the full dependence on the parameters. And here I'm showing the same plot for a specific radius, so mr equal to 5. And we found this analytical expression here that matches really well the behavior we were seeing. So here the points are the semi-analytical method, and the analytical expression given here is given by the red line, basically. So yeah, very good match. Using this asymptotic solution, we can call it, we compare the relaxation times to stationary configurations with the deviation of a straight path for the Earth. So basically, we are comparing how the field relaxes with the acceleration of the Earth. And what we saw is that in a wide range of the parameter space, the relaxation is fast. So this wide region here basically tell us that for most of the masses, the relaxation is fast enough. Here in the red one, no, but the field will basically relax kind of slow. This is what we will expect in principle, because for higher masses, we expect the field to take longer to relax. Yeah, so let me just finish doing some last remarks. We have seen that the presence of the Earth can affect sensitivities of direct detection. We have seen that in the case of couplings that are proportional to the gradient, the sensitivities are going to be enhanced. And this is, for instance, the case of CASPEr wind. And in the last part, we have seen that for most of the mass range of interest, stationary solutions are a good approximation. So yeah, thank you very much, and I hope you enjoyed the talk.